Welcome learners and math lovers in the series of course on topology. We have seen the continuity of a function. We have seen also pasting lemma and the inclusion maps wherein we saw whether they are continuous or not and how to use pasting lemma. Now today we will go for another topic, something called as homeomorphism. Homeomorphism. Now there is a distinction between homomorphism and homeomorphism. Homomorphism you might have studied in your group theory, right? But this is not homomorphism, this is called homeomorphism, H-O-M-E-O, homeomorphism. And let us first define this definition. For homeomorphism, let us take two topological spaces. So let X and Y be two topological spaces. Then a function, a map, say f from x to y is called homeomorphism. Homeomorphism if there are 3 points. The first one, if first f is bijective, f is bijective, so we need to show that f is a one-one function and onto function. One-one function means two distinct points goes to distinct points, right? That means if you have 2 points in the domain, it should not go to the same point in the codomain. And onto means if you take any point in your codomain, it should have a preimage. So first point, f has to be bijective. Second point says f is continuous. So again you need to check the continuity of the function. Okay, and third point says not only f is continuous but f inverse exists because first point itself says f is bijective. So if f is bijective, there exists some inverse of it. That inverse, that is f inverse, is, again let us write from where to where. So f inverse is a function from y to x. So f inverse is also continuous. Okay, and if such a function exists, then we say that x and 2 are homeomorphic spaces, right? Now here there is a distinction. If you remember, for the continuity of a function we have used this notation, but that notation is for the inverse image, and here when we say f raised to -1, this is for the inverse of a function. So f, this notation is nothing but the inverse of function f. Okay, let us take a single example today here. So let us take again one more point here. If f is a homeomorphism from x to y, that is f is a function, that function need not be unique. You can define another function which satisfies this condition, and then we can say that x and y are two homeomorphic spaces, right? So it's not a unique one. So let us take a space, say standard topology, Euclidean topology Ru. Show that the open interval 0, 1 is homeomorphic to open interval 0 to infinity. Homeomorphic. Okay. Now here if you see, both are open intervals, and this is a finite interval 0 to 1 of length 1, and this is the infinite of length infinity. we have to show that these are homeomorphic. That means what are the things we need to show? To show that these two functions are homeomorphic, we have to first we need to find the function f, right? So once we have function f, that function f should be such that f is 1 onto function. It should be a continuous function, and the inverse of that should be again a continuous function. Okay, so we need to define a function. First only we will see. If you have function, then we can talk about the continuity, but if you don't have the function, the continuity will be out of the question. Okay, so for that we need to find f, a function from 0 1 to 0 infinity. How it will be? How will be the function? For example, if we have 0 and 1 here, you need to define a function which will take this 0 1 to 0 to infinity. Continuity and inverse bijective, that also we have to keep in mind. Okay, so you can pause the video and you can search a function which will take you from the interval 0 1 to the interval 0 infinity. Okay, now at 0, it may be like you are defining a function, it is continuous, means there should not be any break. So you may take that 0 to infinity and you can make this 1 to 0, no problem. Okay, but in this interval somehow you have to get infinity. How you will get it? In this interval, when you put either 0 or 1 or in between values, you have to somehow that function should tend to infinity. So for that we can take this 0 and let us take at 0 that should be infinity, that means it should be 1 upon x. So as x goes to 0, this term goes to infinity. And at 1 it should be 0. So when you put x equals to 1 here, it will be 1. So subtract 1 from it. So this function will take 0 to infinity and it will take 1 to 0. Substitute 1 here, you will get 1. 1 upon 1 is 1, minus 1 is 0. So this 1 is mapped to 0. And when you go like this, it will go to infinity. Or when you come like this, it will come like this. Okay, so increasing, decreasing things you can check. So let us let me just like this. So this point will be mapped here, and this point will go to infinity. As x goes to 0, this will go to infinity. So let us define our function to be like. Let us define our function to be defined by fx. If you remember, it is 1 upon x minus 1. If you take 1 minus 1 upon x, then as x goes to 0, that will tend to minus infinity, but not plus infinity. So that is a problem. So we are taking 1 upon x minus 1. And of course, from infinity, if you remove 1, again it makes no difference there. Okay. So this is the first one. First, we have defined the function. First point, to show that f is bijective. That means you have to show that two different points from here will go to two different points here. And of course, to show whether the function is bijective or not, or for example 1 1, you take f at x1 is equals to f at x2 and show that x1 equals to x2. That's the way you show the function is 1 1. So for that let's add this here. For 1 1, let us assume that two images are same. So f at x1 is equals to f at x2. We have to show that if the images in the codomain are same, then the points here in the domain should be same. So f at x1 is defined to be 1 upon x1 minus 1, and this is defined to be 1 upon x2 minus 1. You add 1 to both the sides, this would imply 1 upon x1 is same as 1 upon x2, and if the reciprocal of two numbers are same, this implies x1 equals to x2. This implies f is 1 1 function. Okay, for onto you need to take a point in your codomain. So you take up a point over here. Let us take y. So let us take y in, let y belongs to 0 to infinity. We need to show that there exists some x in our domain. So that means there should exist a number from 0 to 1 such that f at that point should be equals to y. Okay, and for that let us take a part this side. So for that let us take a point, assume that fx is equals to y. Let us assume it and let us check what is the value of x. So if fx equals to y, this implies 1 upon x minus 1 will be equals to y. This implies 1 upon x will be equals to y plus 1, and this implies x will be equals to 1 upon y plus 1. Next point, we got the x, right? If you check the value of fx, all this is a rough cut. Okay, this is the value of x, first one. Second one, let us check what is fx here now. Fx 1 upon y plus 1 we have to check, and this has to be equals to y. This is defined to be 1 upon y plus 1 minus 1, and this is y plus 1, and this is minus 1, and this becomes y. So you have a point which is equals to 1 upon y plus 1 whose image is y. But that is not the only thing. We have to go one more step further, and to show that 1 upon y plus 1 should be in the domain, should belong to open interval 0 1. Then only the function will be onto. It may happen that you have a point whose image is y, but this point is not in the domain, so it makes no sense. Okay, now we have to show that 1 upon y plus 1 belongs to 0 1, and we know that y is in the interval 0 to infinity. So if you see, no matter what y is, 1 upon this 1 is already there, plus y. So this will be a number which is greater than 1, and if it is greater than 1, then of course 1 upon that number will be less than 1, and of course it is not negative. So if it is less than 1, then of course that y will be in the interval 0 1. So I will keep this as an exercise for the viewer to show that. Okay, so this implies f is bijective function. Okay, one part is done. Second part we have to show that f is continuous. Okay, now we have defined fx as 1 upon x minus 1, and we will show that this is the composition of some continuous functions, and we have already proved that composition of a continuous function is a continuous function. Okay, then how you will composite it? How will do it? So first you take x and make it 1 upon x. So your x goes to 1 upon x, and this is the inversion. Okay, and then you take this and translate it by minus 1. So it becomes, this point 1 upon x becomes 1 upon x minus 1. So you translate it, so you will write it as t suffix minus 1. And therefore, we can write, you can easily check that this f can be written as the translation, that is t minus 1 composite inversion function. Okay. So if you want, you can check. We can check what is this. In the rough part, we will verify this. The t minus 1 is a translation and inversion, not identity, inversion of x. This will be equals to translation composite inversion of x. And I of x is defined to be 1 upon x. So translation by minus 1 of 1 upon x. And translation is defined to be that x plus 1 plus a. And in this case, our a is minus 1, so it is 1 upon x minus 1. And that's how we get f. Okay. And therefore, f is equals to t minus 1 composite I, both inversion. You can show that if you don't know. Inversion and translation maps are continuous. Hence, and composition of continuous function of continuous functions is continuous. Hence, f is continuous. Okay. So we have proved two things. We have proved that f is bijective and we have proved that f is continuous. Third point, we need to show that f is invertible. F inverse is continuous. And to show that f inverse is continuous, first we need to find what is the inverse of that f, right? And with our calculation, we have taken that inverse to be f at y is equals to 1 upon y plus 1. So you should know how to find the inverse of a function. Alright. Now, if you noticed, let us take now f inverse is equals to f inverse of y is equals to 1 upon y plus 1. This is how you define your inverse function. If you don't know, then please check how to check whether the function is 1 1, whether the function is onto, and if it is bijective, then how to find inverse of the function. If required, we will go for another video on these topics. Alright. Now f inverse is given by this. To show that f inverse is continuous function. How we will show that f inverse is a continuous function? Again, we will go for the compositions. Now that composition will be, first you take whatever y you have, you translate it by plus 1, and answer what is that y plus 1, we inverse it, right? So invert it. So your y will first be goes to y plus 1, and then y plus 1 will go to 1 upon y plus 1. So this is translation by 1 and this is inversion. So you can write your f inverse as I, that is inversion composite translation by 1. So if you notice, first you make this operation, right? Then you go and make this operation. So you go reverse way. So f inverse is nothing but composition of I composite t1, hence both are continuous functions and hence f inverse is continuous. You write that f inverse is continuous. You can make a note of it. So if you notice here now, Sequentially, we first proved that f is a bijective function. Secondly, we have proved that f is a continuous function. And thirdly, we also proved that f inverse is also a continuous function. Right? These 3 points will say that will say that f is bijective, continuous, and f inverse is continuous. This shows the two intervals whatever we have in usual topology. This implies the two intervals, the domain and the codomain, open interval 0 1 and open interval 0 to infinity, are homeomorphic. Okay. Now also, this is not only with open interval 0 1 and open interval 0 infinity. We can I can do an exercise show that open interval 0 1 and minus infinity to 0 are homeomorphic. So you have to define a function from 0 1 to minus infinity to comma 0, which is a bijective function. F is continuous and f inverse is also a continuous function. So if you can find that, then you can show that this open interval 0 1 and minus infinity to 0 is a continuous is a homeomorphic, or 0 1 is homeomorphic to minus infinity 0. Another exercise you show that we have taken the 0 1. So this 0 1 need not be with 0 infinity. This is, we write homeomorphic to, you take any finite interval. Okay, 0 1 and AB. Next, you show that you take any finite intervals a b, it will be homeomorphic to c. Okay. Now, if you show this, then we already proved that. Again, let me write this also. We can show that AB is homeomorphic to 0 infinity. Likewise, there are many. Let me state all. And finally, or else we can prove that. So that open interval minus 1 to 1 is homeomorphic to R. Okay. Sometimes we write these two lines. So let's use this homeomorphism for 2 lines. Okay. So in all these cases, you define a function f, which is a bijective function. F is continuous. F inverse is continuous. So this is all about this homeomorphism over here. In the next video, we will show that the open balls in Rn, the open balls around 0 of radius 1 is homeomorphic to open ball around A of radius 1. It means if you change the origin, that is the center of the two open balls with the same radius, both are homeomorphic. So we will define a function which will take those points from one open ball to the another open ball. Okay, so see you in the next video.